Okay, everyone. I think we're going to get started again. First of all, I wanted to extend my thanks and appreciation for all of you to take time of your schedules to come and attend our summit today. My name is Joe Kava. I'm with Google, and I help to lead our teams that are responsible for construction and operations of our global fleet of data centers. Along with our large production data centers, we also have several smaller network POPs and computer server rooms around the company. And they were really maybe not operating as efficiently as they should be. Actually, Paulo, we have the clicker. Oh, thank you. Yeah. So, our team has built up a lot of experience over the past several years doing efficient design and operations of data centers. So we took this as a challenge to go into these network POPs and do an efficiency makeover to show what could be done. And our goal was to use inexpensive, everyday, ordinary materials, no custom technology, nothing exotic, nothing sexy, nothing pretty, but just to really go in there and get it done. And the objective was to substantially reduce the PUE, and thereby reduce our energy consumption and ultimately save money. At the beginning, I think like many of you, there's different business units, and different business units design their server rooms with different requirements. In this case, our requirements were to design for ultra-high reliability and availability. These were typical 2N UPS backed up power distribution systems, multiple redundant cooling systems. They were moderately sized, designed for about 250 kW of mixed IT deployments. So there was going to be some higher density equipment, some lower density equipment, all commercially available equipment. So these requirements really look like what I expect most of your data center requirements look like. And as a result, the efficiency of these was not very good right up front. So I'm going to present a case study that is based on the makeover of one of these network POPs. But this has been repeated 5 times in 5 different geographies and with all the same similar results. So in the beginning, this is what they looked like. Looked very much like a traditional server room that you would find in any corporate environment. They were way overcooled. There were multiple redundant CRAC units, all of them on all the time. UPS batteries were on the floor, and of course the UPS batteries require temperature control, stringent temperature control to maintain the availability and reliability of those UPS systems. So they had to be maintained at less than 25 degrees. There was lots of air mixing. As you can imagine from the picture we just saw, there was not good deployment of hot aisle, cold aisle separation. The general best practices that we've talked about this morning that everybody knows weren't implemented properly. The CRAC units were fighting each other, right? They have their own local controllers, and they were set to humidify and dehumidify and cool and reheat the return air. And in one area, the CRAC was dehumidifying. In another area, it was humidifying. It was reheating and cooling. And they were really fighting each other, and it was terribly inefficient. And the result was that the starting PUE was 2.4. So there was a lot of area for improvement here. And once again, I think that it's probably a similar condition to what many of your small data centers look like. This is not atypical. So the first step was to do some modeling. We make extensive use of computational fluid dynamic modeling, and this helps us to visualize the airflow so that we can really see what's going on. And as we suspected, most of the airflow in the starting condition was blowing right by the IT cabinets and being completely wasted. It was terribly inefficient and just really a waste of energy. We also did some thermal modeling. And as I mentioned, this was set up for mixed deployment, so we had some higher density cabinets and lower density cabinets. And this is not even extreme density stuff. This is very typical, 5.5 kW all the way down to 1 to 2 kW per cabinet. So they were Set up on this picture, you'll see that the higher density cabinets were really on one side of the room, on the left side of this picture, and the lower density cabinets were on the right side. And to make it even worse, some of the higher density cabinets were exhausting directly into the return air intake of the CRAC unit, which was, of course, causing that CRAC unit to work harder than it should have. It was seeing an artificially high temperature in the room, and it was turning up all of its compressor stages. So it was really inefficient. So very much in the spirit of being googly, we went and just got things done. So we started our retrofit right away. And the first thing is that we went to work on the immediate improvements that did not require any capital investment, that didn't require extensive engineering analysis or extensive resource use. These were the low-hanging fruit, the things that you can just go in and do immediately. The first was to optimize the airflow coming out of the perf tiles. So optimize the perf tile distribution so that you're balancing the cooling with where the heat load is. The second thing was that we have business units that were responsible for these network pops. So we went to the networking team and the Corp IT groups. We got their alignment to really get their buy-in to start operating these rooms at the expanded ASHRAE recommended range for both temperature and utilizing the full range of recommendation for humidity control as well. The next thing is that we established critical monitoring points so that we could really understand what the temperature distribution was like in the cold aisle. So we set up monitoring points in front of the higher density cabinets, in front of the lower density cabinets, and most importantly, in front of the UPS battery cabinets, so that we had a good profile, a good understanding of the temperature distribution, and that way we would use that, the measurements are always the first step, knowing what you have. So we use that as our baseline so that we could track our improvements and make sure that we weren't exceeding any temperature requirements that were going to jeopardize the equipment. Next, we actually increased. We increased the CRAC set point. So we went and turned up the thermostat. So we now set it to 27 degrees, where it previously had a set point of 22 degrees. And lastly, we implemented improvements in the functionality of the CRACs. I had mentioned that they were set to local control, to humidify and dehumidify. So we disabled the dehumidification, and we decreased the relative humidity set point and increased the sensitivity so that they didn't turn up compressors as quickly as before. They would allow a higher operating range before they increased more mechanical cooling. We also made use of the intelligent control algorithm that was built into these units, and really these units did have unloaders on the compressors. So the intelligent control algorithm, instead of when it sees that the temperature is too high in the room, instead of turning up all the compressors on the unit, it would turn up one more stage and monitor and see what the temperature was, and if it needed to, then it would turn up another stage. So it was really a more intelligent way of managing the cooling. So these immediate fixes, we saw a reduction in PUE from 2.4 to 2.2. So we knew we were headed in the right direction. So far we've spent $0 and we've spent very little energy getting this done. I mean, manpower. We just went in and did it. The next step was to work on some medium-term improvements. And these are ones that required a little bit more analysis, a little bit of engineering effort, and a little bit of money. But you'll see it was a very modest amount. We first focused on good cold aisle containment. We investigated a full containment solution. There's many commercial products available now that have lids over the cold aisle. They're fusible link lids. But the problem that we encountered is that we were doing these upgrades in various different geographies where there were multiple authorities having jurisdiction, and they had opinions about this. And some of those opinions were that you can only do that if you modify the current sprinkler system. And in one specific case, the authority wanted us to drop the sprinkler system down low enough so that it was within the cold aisle containment. Well, we were doing this work on a live data center, live server room. And we did not allow for any shutdown of any of the equipment. So in our opinion, working on an active sprinkler system above live IT equipment was probably a little bit too risky for what we wanted to do. So we decided to let's just focus on the best practices first without a full cold aisle containment. We can get a majority of the way with just the best practices of just isolating and separating hot aisle from cold aisle. So simple things, blanking plates on the partially populated IT cabinets, end panels on the cabinets that were at the end of the row. We also fitted 1.2 meter tall extensions, return air extensions onto the CRAC units, and that was to prevent the warm air from discharging directly into the CRAC air intakes. And we also did some things with the lighting load. We implemented sensors, automatic sensors that would turn off the lights when the rooms were unpopulated. You know, simple things like that. But you know, they were low cost, easy to do, and we modeled all of this with our CFD modeling. I mentioned we have this capability in-house. If you don't, it can be easily contracted out for a very modest amount of money, you know, around $5,000 or $10,000, you can get good CFD modeling done. And most importantly, we turned down the unneeded cooling. So we turned down the stages of the compressors that weren't needed. And this had a pretty dramatic reduction in the PUE from 2.2 down to 1.7. I mentioned that we added these 1.2 meter tall return air extensions to the CRACs. This is what the thermal profile looked like without the extensions. And on the left side of this picture, you'll see where the hot spots were in this room. And that was because you know, these higher density racks, they were really discharging right into that CRAC unit there, you can see. So with the extension, on the right side of this room, you see this picture where now we have a much more balanced temperature distribution. The temperature, the air is more stratified, and we're taking in more evenly, you know, more even temperature air at the CRAC air intakes. These were very simple, inexpensive, just sheet metal, bent sheet metal, fabricated extensions, and they proved to be pretty effective. We also, I mentioned that we turned down unneeded CRACs. So in this case, this shows what the temperature profile looks like in the cold aisle with only 2 of the CRACs running. So on this picture, the upper left-hand and the lower right-hand CRAC units are turned off. And you see that because we had very modest load at this time in this room, we still had totally sufficient cooling. In the cold aisle, we were maintaining our temperature set points well. We didn't have any, you know, any hot spots in the cold aisle, and so we were able to completely operate in this condition. I talked about establishing our critical monitoring points. On this floor plan diagram, it shows that where the monitoring points were set, they're represented by the circles on this diagram. So we were monitoring in the cold aisle at an elevation of 80 centimeters above the raised floor. And we were monitoring in front of the higher density cabinets and the lower density cabinets, and most importantly in front of the UPS battery cabinets as well. So we use this data now to establish that we were maintaining our cold aisle temperatures properly, and this ultimately became the feedback loop for an improved control algorithm for the CRACs that I'll talk about next. So as part of our longer term improvements, we, in addition to adding those temperature monitors in the cold aisle, we went out and bought a commercially available master PLC controller so that we could control all the CRACs in unison, as opposed to local control. We now had a master controller, and really what that allowed us to do is operate in kind of an N+2 condition. So we had only N CRACs online at any given time, but if one CRAC were to fail, the master controller would start up another CRAC, so that we always had redundant cooling, but it wasn't being run when it wasn't needed. In addition to that, we also set some parameters in the control algorithm so that if the IT load increased beyond a minimum threshold, it would turn up additional stages of compressors. And this was, like I said, an inexpensive and a commercially available PLC programmer. So it wasn't customized in any way. So this resulted, with all of the improvements stacked up now, this resulted in a PUE decrease from 1.7 down to 1.5. So after all of these retrofits, this is what the post-CFD analysis looked like. And you compare this to the initial one at the earlier part of the presentation, and now your cold air is actually working for you. All the cold air is going through the IT cabinets and doing the work that's intended to do. We're not getting blow-by. We're getting even return air back to the CRAC extensions. So the final results, they demonstrate a strong adherence to the best practices that we heard Zal and Harks this morning talk about from the Green Grid and Code of Conduct, all the things that we know that we're supposed to do. And while maybe we've gotten past the theory of what it takes to get lower PUEs, in many cases we as an industry haven't gotten into the practice yet. So this represented getting into the practice, going in there, rolling up your sleeves, and just doing it. As I mentioned, we had blocked off all the cold aisles with containment. You'll see some pictures of the freezer, the freezer sheets, the plastic meat locker curtains. And all of this work was done without any IT equipment shutdown. So this was all done on live operating network rooms. So here's some pictures. Of course, blanking plates, pretty simple, not very sexy, but pretty effective. The meat locker curtains at the end of the cold aisles. This was, once again, very inexpensive, easy to install, and didn't require any equipment shutdown to implement this. Also, we fully contained the UPS units with these meat locker curtains so that we can maintain a slightly lower temperature in front of the UPS battery cabinets and get really good cold aisle isolation right around there. And also, we realized that we have some tall Googlers that sometimes walk with their head down looking at their feet. And so we put some bumpers on the cross-member bracing there to, you know, it doesn't really help your PUE, but it does cut down on your expenses related to aspirin. So that was a pretty simple implementation there too. There was a walkway in the middle of these IT rows, so we sealed that off also with the same meat locker curtains. And this is a picture of the fabricated sheet metal extensions on the CRAC units. Very simple and very industrial, not you know, pretty, but very effective. We've tabulated the PUE results, and this is across the 5 POPs that we've worked on so far. We're waiting on the final data from 2 of them, but we monitor our PUE real time. We take measurements at our power quality meters every second. Every day, our PUE measurements are an aggregated average of more than 86,000 data points. And we've been monitoring this over a period of several months, and it's remained consistent over that period of time. At the beginning of the project, the actual utilized kW power in the room was 80 kW. At the end, it was 86 kW. So the IT or the PUE improvements were not simply because of increased IT load in the room. And overall, it represents a 0.7 to 0.9 PUE reduction, which if you just look at the cooling overhead component, that's more than a 60% reduction in the cooling overhead in these rooms. Very simple ROI analysis. So a couple of assumptions to point out here. One, we did not include our own labor in these ROI calculations. The reason is that our technicians were supporting these POPs anyhow, so it wasn't added labor to do this work. And I also mentioned that our CFD analysis is done in-house, so those weren't in this calculation. But on a very modest expense of about $25,000 US per site, we're now achieving over $67,000 in energy savings per site annually. So the ROI is really a matter of single-digit months here, you know, 6 to 9 months. Makes every CFO happy. Really, it's a no-brainer from the cost standpoint. And it really comes down to a matter of we have to stop talking about it and we have to do it. So I encourage all of you that you know what you need to do. If you haven't done it, you can do it on a live data center. It doesn't take sexy or custom technology that only Google or Microsoft or Amazon can do. It's really easy. So just do it. And there's a short video now to go through about these best practices.
Here at Google, data centers are very, very important to us. We've spent a lot of time innovating the way in which we design and build these facilities to minimize the amount of energy that these computing facilities use. There's design choices that you can make for energy efficiency that improve the performance of your data center. And these things are just best practices. They're applicable to small data centers or large data centers. The first step is to focus on the management of the airflow. One thing that we found very useful at Google is CFD analysis to see where are your hot spots and how is your airflow going to actually be directed in your data center. In one of our computing and networking rooms, we did a bunch of other retrofits. All told, we spent about $25,000 in parts, and those $25,000 saved us over $65,000 in energy costs yearly. There really are very simple, effective approaches that all of us can implement to reduce data center energy use.
Thank you very much. There's still a few minutes for questions. Any questions?
Over here in the front.
Hi, Velo Everett again from Everett Engineering in Toronto. I was just curious with your CFD modeling. Oh, sorry, is that on? With your CFD modeling, how accurate was it when you actually compared it to the metrics? When you went back, did you recalibrate your models after that, and how accurate were they?
Yeah, very good point. We actually went through several iterations of improving our model. I think it probably took about 4 iterations before we got the model, the modeled airflow actually matching the measurements coming out of the tiles. So so it took a little bit of iteration to get the accurate model, but we absolutely did verify that.
And just to clarify on that, what was it that you had to adjust in the, you're using someone like Six Sigma, I guess?
In the model?
Yeah.
So to be honest with you, I'm not the expert in that area. I can go back and talk to our modeling team, our software modeling team. I don't know exactly what had to be changed.
Hi, very interested to know what happened to the humidity after you turned off the dehum and you opened the window.
Sure. So these networking rooms are in larger buildings, and the buildings themselves are actually pretty well sealed. And the makeup air is handled at a common air handling unit. So allowing the humidity to go from 20 to 80% relative humidity, using the full expanded ASHRAE operating range, we found that we didn't need to do local humidification control, that the air handling makeup air units were sufficient.
Okay. My question had a secret meaning, didn't it? And I didn't make it clear. In the fully allowable or permissible range of 20 to 80, in the same document there's actually a warning about using going above 60% RH for long periods of time because it damages the hardware. I just wondered what your room actually settled down to. Did it because I mean above 60% RH is quite humid anyway, but you don't know what it actually settled down to in terms of the
I don't have that data at the top of my head. I know that initially the set points were very restrictive, 45 plus or minus like 10, but I don't know what it settled out at. I do know that we're not having excursions outside of the operating range, but I can't actually update that with our current data.
More questions? Mark?
Okay.
Just to keep the questions right here in the middle, Joe. We'll, anybody else in this row want to ask one, we can add another. But your estimate of the 5 to 10K for the CFD modeling, that was for the initial model plus the rerun after, or as many times the iterations?
Yeah,
as it took you?
I think with that you'll be able to get a couple of iterations so that you can you can improve and verify your model. It's not really that expensive. There's a lot of companies that offer this as engineering services.
Yeah.
So if you don't have it in house, we believe that it's a really important component because you need to be validating what you're doing,
Right.
all along the way.
And then you mentioned that, but you just started doing things. So did you start to do some of your step 1, 2, and 3 before the initial CFD was complete, or did you run a CFD, then you had at least basic results to be able to go?
So the the initial things that we just knew were wrong right off of the bat, we just did. And then we went in and did the modeling to verify where we were at before we took any of the more aggressive steps. And it was, when you go into this and you take a data center professional into a room and they just know that your perf tile distribution is wrong based on where the heat load is, those are things that you can just do without really having to model first, right?
Since this is the row of the questions, I'll ask the next one. So my name is Ronald. How long did it take you from the initial idea, let's start looking at this and do something, until your final retrofit?
All told, I think that the retrofits were about a 3-month project, all told. But we've been gathering data on the performance of these for in excess of 6 to 8 months, depending on which of these rooms were done first. So and we did it in steps, right? So if we had done everything right off the bat all at once, we could have got the retrofits done a lot sooner. But we were letting it settle out and measure each step of the way. So so it took about 3 months. Okay.
One more question.
So you said that you didn't include your labor costs into
Right.
the 25K estimate. Roughly, you got an estimate of how many man months you would have you spent in this?
Over that period of 3 months retrofit, we weren't using labor all the time, obviously, because you go in and maybe you spend a couple of days working, and then you're measuring and allowing the room to stabilize, and you're measuring for a while before you take the next steps. Overall, I would say that it may have been on the order of a few man weeks, 3 or 4 man weeks to do all the work. You get the sheet metal stuff fabricated offsite. It's pretty inexpensive and easy to do. Fitting it, really pretty simple. So none of this that was implemented really takes a lot of man labor to do.
All right. Thank you very much, Joe.
Okay. Thank you very much.